There is an immense literature on attacking block ciphers. In this segment, I just want to give you a taste for what these attacks look like, and I hope I'll convince you that you should never, ever design your own block cipher and just stick to the standards like triple DES and AES. The first set of attacks I want to talk about are attacks on the implementation of the block cipher. As an example, imagine you have a smart card that's implementing a block cipher. So the smart card, for example, could be used for credit card payments and might have a secret key inside of it to authenticate your credit card payments as you stick the card into a payment terminal, say. So now if an attacker obtains your smart card, what he could do is he could actually take the smart card to a lab and then run the card and measure very precisely how much time the card took to do encryption and decryption. Now, if the amount of time that the implementation took to do encryption depends on bits of the secret key, then by measuring the time, the attacker will learn something about your secret key, and in fact, he might even be able to completely extract your secret key. And there are many examples of implementations that simply by measuring the time very precisely for many operations of encryption algorithm, you can completely extract the secret key. Another example is rather than just measuring the time, you could actually measure the power consumption of the card as it's operating. So literally, you can connect it to a device that will measure the current that the card is drawing and then graph the current very precisely. Now, these cards are not very fast, and as a result, you can actually measure the exact amount of power consumed at every clock cycle as the card was executing. When you do that, you actually get graphs of this form. So this is an example of a smart card operating while it's doing the DES computation. So you can see very clearly, here's when it was doing the initial permutation, here's when it's doing the final permutation, and then here you can count there are actually 16 hills and troughs corresponding to the 16 rounds. And essentially when you zoom in on a graph like this, you can basically read the key bits off one by one just by looking at how much power the card consumed as it was doing the different operations. It turns out that even cards that take steps to mask this type of information are still vulnerable. There's an attack called a differential power analysis, where basically you measure the power consumed by the card over many runs of the encryption algorithm. And as long as there's any even small dependence between the amount of current consumed and the bits of the secret key, basically that dependence will show up after enough runs of the encryption algorithm, and as a result you'll be able to completely extract the secret key. Okay, so these attacks were actually discovered by Paul Kocher and his colleagues up at Cryptography Research, and there's actually a fairly large industry devoted to just defending against these power attacks. As far as timing attacks are concerned, I want to mention that these are real. They're not just about smart cards. For example, you can imagine a multi-core processor where the encryption algorithm is running on one core and the attacker code happens to be running on another core. Now, these cores actually share the same cache, and as a result, an attacker can actually look at the exact cache misses that the encryption algorithm incurred. It turns out that by looking at cache misses, you can completely figure out the secret key used by the algorithm. So one core can essentially extract information from the other core just by looking at cache misses. So implementing these block ciphers is actually quite subtle because you have to make sure that the side channel attacks don't leak information about your secret key. Another type of attack that's been discussed in the literature is what's called a fault attack. So here, basically, if you're attacking a smart card, you can actually cause the smart card to malfunction, perhaps by overclocking it, perhaps by warming it up. Essentially, you can cause the processor to malfunction and output erroneous data. It turns out that if during encryption there are errors in the last round of the encryption process, that the resulting ciphertexts that are produced are enough to actually expose the secret key K. It's quite an interesting result that in fact if you have any errors, if you ever output a wrong result, that actually could completely compromise your secret key. So of course the defense against this means that before you output the result of your algorithm, you should check to make sure that the correct result was computed. Now of course that's non-trivial, because how do you know that the error didn't happen in your checking algorithm? But there are known ways around that. So basically you can actually compute something 3 or 4 times, take majority over all those results, and be assured that the output really is correct as long as not too many faults occurred inside of your computation. These are attacks on the implementation. I hope these examples kind of show you that not only should you not invent your own block ciphers, you should never even implement these crypto primitives yourself, Because A, you have to make sure there are no side channel attacks on your implementation, and B, you have to make sure that the implementation is secure against fault attacks. Okay, so instead you should just use standard libraries like the ones available in OpenSSL and many other libraries out there. So don't implement these primitives yourself, just use existing libraries. Alright, so now I want to turn to kind of more sophisticated attacks on block ciphers, and I'll particularly talk about how these attacks apply to DES. Okay, so these attacks were discovered by Biham and Shamir back in 1989, and I'll particularly describe a version of the attack discovered by Matsui in 1993. So the goal here is basically, given many input-output pairs, can we actually recover the key better than exhaustive search? So anything that runs better than exhaustive search already counts as an attack on the block cipher. Okay, so the example I want to give you is what's called linear cryptanalysis. And here, imagine it so happens that C is the encryption of M using key K. And suppose it so happens that if I look at a random key and a random message, somehow there's a dependence between the message, ciphertext, and the key bits. In particular, if I XOR a subset of the message bits, so this is just a subset of the message bits, if I XOR that with a certain subset of the ciphertext bits, so these two the attacker sees. The attacker has the message and the attacker has the ciphertext. And then you compare that to an XOR of a subset of the key bits. Now, if the two were completely independent, which is what you'd like, you definitely don't want your message and your ciphertext to somehow predict your key bits. If the two are completely independent, then this equality will hold with probability exactly 1/2. But suppose it so happens that there's a bias, and this probability holds with probability half plus epsilon for some small epsilon. It so happens that in fact for DES, there is such a relation. The relation holds specifically because of a bug in the design of the 5th S-box. It turns out the 5th S-box happens to be too close to a linear function, and that linear function basically, as it propagates through the entire DES circuit, generates a relation of this type. You notice this is basically a linear relation that's being computed here. So this small, tiny linearity in the 5th S-box generates this relation over the entire circuit where the epsilon is tiny. Epsilon is 1/2^21, and I wrote down what that is. So the bias is really small, but nevertheless there is a bias using these particular subsets of bits. Now I'm not going to show you how to derive this relation, or I'm not going to show you even what it is. I'll just tell you how to use a relation like this once you find it. Okay, so here's our relation that we have, and the question is how to use it. So with a little bit of statistics, you can actually use an equation like this to determine some of the key bits. And here's how you do it. Suppose you were given 1/epsilon² message ciphertext pairs, and these have to be independently random messages and the corresponding ciphertexts. What you would do is you would use the formula above. In fact, you would use the left-hand side of the formula above to compute this relation between the message and ciphertext for all the pairs you were given. Now, what do you know? You know that for half plus epsilon of these values, you know that these things will be equal to an XOR of the key bits. So if you take majority over all the values you've computed, it turns out it's not so difficult to see that in fact you'll get the correct prediction for the XOR of the key bits with probability 97.7%. In other words, if this relation happens to be correct more than half the time, then the majority will be right. And because there's a bias, there's an epsilon bias, the probability that you will be correct more than half the time